It has been 2 years since NASA's James Webb telescope gave us a stunning first look at the depths.
This is the first time we get to orbit Mercury.
Seeing a universe we've never seen before. We thought it was there, we hoped it was there, but now we see it for the first time.
James Webb has revolutionized our understanding of the universe, unveiling galaxies and stars in previously unimaginable detail. But what's rarely discussed is its potential to unravel mysteries closer to home, such as the secrets of Mercury. This tiny, enigmatic planet has puzzled scientists for years, and while Mercury was once perceived as a simple, scorched rock too close to the sun for much scientific intrigue, recent discoveries suggest that this is far from the truth. In a stunning revelation, the James Webb telescope may have detected something NASA is hesitant to fully disclose, a discovery so unnerving that, if true, it would shatter previous beliefs about our own solar system. Join us as we dig deep into the most intriguing discoveries of Mercury that could blow your mind. Mercury has often been shrouded in mystery. As the innermost planet, its proximity to the sun places it within 2 hours of sunrise or sunset, making it elusive in the night sky. This closeness to the sun means Mercury never appears when the sky is fully dark, as it rises and sets just before or after the sun itself. These factors combined have made Mercury a mysterious figure in planetary science and astronomy since ancient times, though its bright, speedy path in the sky has fascinated humanity for thousands of years. The Sumerians, who lived over 5,000 years ago, were among the first to record sightings of this elusive planet. Later, the Greeks, who were masters of mythology and celestial observation, gave Mercury dual names depending on its timing in the sky. Apollo, when it was visible as the morning star, and Hermes when it appeared as the evening star. Hermes, known as the messenger god who moved swiftly between the heavens, the earth, and the underworld, symbolized Mercury's rapid orbit compared to other celestial bodies, racing across the sky in a mere 88 Earth days. Roman astronomers later adopted Hermes' name in the Latin form, calling the planet Mercury, which is how we know it today. This speed and brightness, though striking, have remained hidden to many observers, even seasoned astronomers, over centuries. The renowned astronomer Nicholas Copernicus, who revolutionized our understanding of the cosmos with his heliocentric model in the 16th century, lamented on his deathbed that he had never actually seen Mercury. The challenges of observing Mercury extended far beyond ancient and medieval times. The planet remained largely enigmatic until the 20th century. Scientists struggled with unanswered questions, such as the length of Mercury's day, which wasn't accurately measured until the 1960s. Earth-based observations were often hindered by Mercury's proximity to the sun. Observing the planet through telescopes, even with modern equipment, was impeded by the sun's blinding light and Earth's turbulent atmosphere, which blurred the view. The Hubble Space Telescope, a premier tool for deep space observations, couldn't safely point near the sun to observe Mercury due to the risk of its sensitive instruments being damaged by sunlight. For these reasons, Mercury remained an uncharted frontier in many ways until spacecraft technology advanced enough to take on the formidable challenge of exploring it up close. In 2004, NASA launched the MESSENGER, also known as Mercury Surface, Space Environment, Geochemistry, and Ranging Probe, a pioneering mission to explore Mercury in detail. After a complex series of maneuvers, which included gravity assists from Earth, Venus, and Mercury itself, MESSENGER finally entered Mercury's orbit in 2011. This was no small feat. Traveling to Mercury required overcoming the intense pull of the sun's gravity, which meant using far more energy and planning than missions to outer planets. Over the next 4 years, MESSENGER completed its ambitious mission, mapping Mercury's entire surface and gathering a wealth of data that answered long-standing questions and revealed new mysteries. The probe's journey ended in 2015 when it intentionally crashed into the planet's surface, leaving behind a legacy of discovery that has reshaped our understanding of Mercury's unique characteristics. At first glance, the surface of the planet looks similar to the cratered terrain of the Moon, an impression reinforced by the roughly comparable size of the two bodies. However, Mercury is far denser, a feature that reveals much about its composition. Beneath Mercury's rugged, cratered exterior lies a vast metallic core that takes up a staggering 61% of the planet's volume, compared to only about 4% on the Moon and 16% on Earth. This iron-rich core has been a source of fascination for planetary scientists because it provides clues about Mercury's formation and evolution. Additionally, Mercury's surface exhibits dramatic differences from the Moon's, including the absence of large, dark volcanic plains known as maria, which are prevalent on the Moon. Instead, Mercury's surface is marked by wrinkles and cliffs, called scarps, which indicate that the planet is slowly contracting as it cools, a phenomenon that doesn't occur on the Moon. Mercury's extreme nature extends to its position as the closest planet to the Sun. With an average distance of just 58 million kilometers, its orbit is the shortest of all the planets, completing a full revolution around the Sun every 88 Earth days. The result is that Mercury experiences the most intense solar radiation of any planet in the solar system. Its small size further sets it apart. Mercury's radius is approximately 2,440 kilometers, making it the smallest major planet, smaller, in fact, than Ganymede, Jupiter's largest moon, and Titan, Saturn's largest moon. This diminutive stature, however, does not make Mercury insignificant. It possesses a mean density that rivals Earth's, despite having much less mass. This high density, when adjusted for the lack of compression from gravity, which would be greater on a more massive body, makes Mercury the densest planet in our solar system, revealing its composition as exceptionally metal-rich. The planet's massive iron core extends from the center to a radius of about 2,100 kilometers, covering approximately 85% of the distance to the surface, with a rocky mantle and crust only about 300 kilometers thick. Observing Mercury from Earth presents unique challenges. Its close proximity to the Sun means it is usually only visible around dawn or dusk, never straying more than 28 degrees from the Sun's position in the sky. Mercury's orbital pattern, known as its synodic period, repeats roughly every 116 days, bringing the planet back to the same relative position in the morning or evening sky. Because Mercury often hovers low on the horizon, observers on Earth must peer through dense layers of Earth's atmosphere, resulting in a blurred view of the tiny planet. Even space telescopes, such as the Hubble Space Telescope, are limited in their ability to observe Mercury due to the Sun's intense glare, which can damage sensitive instruments. On rare occasions, Mercury crosses directly between Earth and the Sun in an event known as a transit. These transits, which occur about 13 times per century, allow scientists to observe Mercury as a small dark disk moving across the Sun's bright surface, providing unique observational opportunities. Sending a spacecraft to Mercury is a formidable task due to the planet's location within the Sun's intense gravitational field. The journey requires careful planning and an enormous amount of energy to ensure that the spacecraft's trajectory aligns with Mercury's orbit, allowing it to enter orbit around the planet rather than merely speeding past it. The first mission to achieve a close approach was Mariner 10, launched in 1973, which utilized a gravity assist maneuver from Venus to reach Mercury. Mariner 10 flew by Mercury 3 times between 1974 and 1975, capturing the first close-up images of the planet. Following Mariner 10, the Messenger mission was meticulously planned to use a series of gravity assists, involving flybys of both Venus and Mercury, to reach the correct trajectory and velocity to enter orbit in 2011. The spacecraft's elongated orbit allowed Messenger to study Mercury's surface and magnetic field in unprecedented detail, despite the intense heat from the Sun and the planet's own re-radiated warmth, which posed significant thermal challenges to the spacecraft's instruments. The scientific insights from the Messenger mission transformed our understanding of Mercury. A significant surprise was the discovery that Mercury has a magnetic field, a finding that contradicted prior expectations. According to the prevailing theory, a planet needs a rapid rotation and a molten core to generate a magnetic field. Mercury's rotation is slow, taking 59 Earth days to complete a single rotation, and its small size suggested that any molten core would have solidified billions of years ago. However, Messenger detected a magnetic field, suggesting that Mercury's core remains partially molten. Additionally, Messenger's observations revealed that the magnetic field is asymmetrical, being about 3 times stronger in the northern hemisphere than in the southern hemisphere. Some scientists theorize that Mercury's iron core may be crystallizing from the outside inward, a process referred to as iron snow. According to Christopher Russell, a professor and researcher, this phenomenon could resemble a snowstorm within the core, with iron crystals snowing throughout the fluid, gradually solidifying and generating a magnetic field. Ground-based radar observations in 2007 also supported the idea that Mercury's core remains at least partially molten, potentially accounting for the persistence of the planet's magnetic field. Although Mercury's magnetic field is only about 1% as strong as Earth's, it remains surprisingly active, interacting with the solar wind in unique ways. The interaction between the solar wind's magnetic field and Mercury's own field generates magnetic tornadoes, funneling high-energy plasma from the solar wind down to Mercury's surface in intense transient bursts. In another unexpected discovery, Mariner 10 detected a faint atmosphere known as an exosphere around Mercury. Scientists had long assumed that a planet as small and hot as Mercury could not retain an atmosphere, but Mariner 10's spectral measurements identified atomic helium and hydrogen near the planet's surface. These atoms are largely derived from the solar wind and quickly escape into space. Later, telescopic observations revealed the presence of additional elements like sodium, potassium, and calcium, likely originating from Mercury's surface through processes such as meteoroid impacts and solar wind bombardment. These particles tend to accumulate on the planet's night side but are dispersed each morning by the sun's intense radiation. The Messenger spacecraft, equipped with ion detection instruments, allowed scientists to observe a range of ions in Mercury's exosphere, including oxygen, sodium, magnesium, potassium, calcium, and sulfur. Another instrument on Messenger mapped Mercury's comet-like tail, which is especially prominent in sodium emissions and extends deep into space, further demonstrating the dynamic nature of Mercury's thin exosphere. One of the most astonishing findings from ground-based radar in the 1990s was the discovery of highly reflective patches at Mercury's poles, hinting at the presence of water ice, an astonishing possibility given Mercury's proximity to the Sun. These bright patches appeared in the polar regions, specifically within deep craters that remain permanently shadowed. This is crucial because, while sunlight heats Mercury's exposed surface to extreme levels, these craters, located at latitudes that never receive direct sunlight, create cold traps. The absence of sunlight in these areas allows temperatures to drop to levels cold enough for water ice to exist without immediately sublimating. Initial excitement about these reflections was tempered by caution, as it was difficult to confirm the exact nature of these reflective areas from Earth-based observations alone. In 2008, NASA's Messenger mission entered orbit around Mercury, offering a closer, more precise look. Using advanced instruments capable of scanning Mercury's surface and analyzing its composition, Messenger provided confirmation in 2012 that these polar reflectances were indeed deposits of water ice. Messenger's findings showed that this ice lay hidden under a layer of dark organic material, acting as a natural insulator against the surrounding heat. These organic compounds, likely delivered by comet and asteroid impacts, effectively shield the ice from sublimation by both moderating temperatures and reducing its exposure to solar radiation. The presence of water ice on a planet as close to the Sun as Mercury defied conventional expectations. Scientists had presumed that any water on Mercury would be destroyed by intense solar radiation or otherwise lost to space. However, Mercury's unique geography and history of comet and asteroid impacts have created conditions conducive to the accumulation and preservation of water ice. Evidence now suggests that, over billions of years, Mercury has been periodically showered by water-rich objects. When these bodies impact the planet's surface, they release volatile compounds, including water. Though much of this water escapes Mercury's low-gravity environment or is vaporized by solar radiation, some water molecules manage to survive by migrating across the surface. Mercury's weak atmosphere, known as an exosphere, is tenuous and incapable of supporting water in a gaseous state. As a result, water molecules on the surface hop in a random pattern, bouncing across the terrain. This process, known as ballistic transport, involves water molecules being knocked around by solar winds and other particles, creating a chaotic movement pattern across Mercury's landscape. Occasionally, some of these molecules land within a polar crater's permanently shadowed regions, where temperatures are cold enough for water to freeze. Once settled in these shadowed zones, the water molecules are essentially trapped, building up gradually over time into thick layers of ice. Calculations indicate that this seemingly random process has led to a significant accumulation of ice deposits within these craters. Additionally, a regolith layer, composed of a mix of organic compounds and mineral debris, further protects the ice from the heat of Mercury's environment. This dark insulating layer, likely also a result of comet and asteroid impacts, absorbs and distributes solar energy, preventing direct heat transfer to the ice below. By acting as a natural barrier, it insulates the ice from the extreme surface temperatures outside the crater. This protective layer is integral to the survival of Mercury's polar ice because, without it, the ice would likely sublimate under Mercury's fluctuating temperatures. The discovery of ice on Mercury is remarkable not only for its sheer improbability, but also for what it suggests about planetary science and solar system dynamics. While scientists initially believed that the inner planets, particularly those close to the Sun, were too inhospitable to retain water, Mercury has proven otherwise. The finding supports theories that water and organic compounds, key ingredients for life, can survive under extreme conditions, even in proximity to intense solar radiation. Mercury's ice deposits are also crucial for understanding the delivery mechanisms of water to the inner planets, which may have implications for early Earth's water sources. The existence of water ice on Mercury prompts further questions about the planet's potential for scientific discovery. Studying these polar deposits could offer clues about Mercury's formation and evolution, as well as insights into the frequency and composition of cometary and asteroid impacts in the inner solar system. By analyzing Mercury's ice deposits, scientists may be able to determine the chemical signatures of these water sources, revealing information about the types of materials that contributed to the ice's accumulation. Looking forward, Mercury's icy poles also present intriguing possibilities for future exploration. If humanity pursues in situ exploration, or even resource extraction in the future, the presence of water could be invaluable. Water is a crucial resource for life support, and it can also be split into hydrogen and oxygen for rocket fuel. Though transporting such resources from Mercury would be challenging due to its high gravity and proximity to the Sun, understanding how water exists on Mercury could help develop strategies for utilizing similar resources on other airless bodies, such as the Moon. Another significant feature, Mercury speeds around the Sun every 88 Earth days, traveling through space at nearly 180,000 kilometers per second, faster than any other planet. Its orbit is not a perfect circle. Instead, it follows a highly elliptical path, bringing it as close as 47 million kilometers to the Sun and as far as 70 million kilometers away. This unique orbit leads to dramatic variations in how Mercury is perceived from Earth. When Mercury is at its closest point, known as perihelion, it appears more than 3 times larger in the sky than it does when viewed from our planet. Mercury's peculiar orbit and rotational dynamics contribute to a strange phenomenon for anyone who might stand on its surface. A single rotation on Mercury takes about 59 Earth days, creating a unique visual experience. When the Sun rises, it does not just ascend and move across the sky as it does on Earth. Instead, it briefly rises, sets, and then rises again before finally moving westward. Similarly, at sunset, observers would see the Sun dip below the horizon only to rise again briefly before setting once more. These unusual solar movements stem from Mercury's slow rotation in conjunction with its rapid orbit around the Sun. In 2016, a significant event occurred when Mercury transited across the face of the Sun as observed from Earth. This rare alignment provided valuable data about Mercury's thin atmosphere, contributing to our understanding of this enigmatic planet. Additionally, the transit aided astronomers in their search for exoplanets, worlds beyond our solar system, and allowed NASA to refine its observational instruments. As Mercury orbits the Sun so swiftly, overtaking Earth approximately 3 or 4 times a year, creates an optical illusion where Mercury appears to move backward across the night sky. This phenomenon, known as Mercury in retrograde, lasts for about 3 weeks and is often associated with misfortune and miscommunication in astrological beliefs. Astrologers argue that this perceived backward motion disrupts Mercury's typical influence, which governs communication and intellectual pursuits. Regardless, the mysteries surrounding Mercury extend beyond its orbit and retrograde motion. The planet's surface is marked by large global scarps and wrinkles, first discovered by the Mariner 10 spacecraft in the 1970s and later confirmed by the Messenger mission. These geological features include enormous cliffs that can stretch for hundreds of kilometers and tower several kilometers above the surrounding terrain. In contrast, Messenger also identified much smaller scarps, only a few kilometers long and tens of meters tall. Notably, these smaller features appear geologically young, suggesting that Mercury is not as cold and lifeless as once thought. Instead, the planet exhibits signs of geological activity, driven by the cooling of its hot core, leading to surface deformation. As scientists delve deeper into Mercury's geology, they uncover regions with distinct geochemical signatures, indicating a diverse array of terrains rather than a uniform surface. Messenger's observations revealed the presence of delicate volatiles, including potassium and uranium, elements that should have been vaporized by the extreme heat of impacts or the blistering radiation from the sun. The existence of these chemicals challenges existing theories about Mercury's unusually large core, leaving scientists eager to explore new explanations. Further findings from Messenger revealed pyroclastic flows on the planet's surface, suggesting explosive volcanic activity involving lava that had interacted with volatile gases like water and carbon dioxide. These gases were not expected to be abundant on a planet so close to the Sun, adding another layer of complexity to our understanding of Mercury's geological history. Additionally, radar observations detected water ice hidden in the shadowy craters near Mercury's poles, reminiscent of similar findings on Earth's moon. The Messenger mission concluded in 2015 when the spacecraft, having exhausted its fuel, made a controlled crash into Mercury's surface. This final act left scientists with a treasure trove of data from its 4,1015 orbits, all of which are now under analysis. Researchers aim to piece together a comprehensive explanation of how Mercury formed, taking into account its various characteristics and the clues hidden within the data. One exciting avenue for future exploration is the potential for seismic activity on Mercury. If the planet possesses a hot, liquid core and remains geologically active, any movement of the crust to form new ridges or wrinkles could generate seismic waves. On Earth, scientists utilize seismometers to detect these waves, allowing them to map the planet's interior. During the Apollo missions, astronauts observed moonquakes, providing insight into the geology beneath the lunar surface. NASA plans to apply similar techniques on Mars, deploying a seismometer aboard the InSight lander to explore Martian geology. Applying these methods to Mercury could allow scientists to measure seismic waves and gain valuable information about the planet's core size and structure. Such observations might reveal whether Mercury has a warm, liquid outer core surrounding a solid inner core, similar to Earth. By unraveling these mysteries, we would take significant steps toward understanding Mercury's formation, its current state, and its implications for other rocky planets orbiting distant stars. Another long-awaited mission is Bepi-Colombo. A joint endeavor between ESA and JAXA, it is poised to become the second-ever mission to orbit Mercury and the most complex one to date. Scheduled for arrival at its destination in 2025, Bepi-Colombo is set to illuminate the mysteries of the solar system's innermost planet through its intricate design and sophisticated scientific instruments. At the core of the Bepi-Colombo mission are 2 orbiters: the European Mercury Planetary Orbiter, or MPO, and the Japanese Mercury Magnetospheric Orbiter, or MMO. Together, these orbiters are equipped with a remarkable suite of 16 scientific instruments designed to probe various enigmatic phenomena associated with Mercury. This mission aims to address several intriguing questions that have long puzzled scientists. For instance, do the polar craters of this scorched planet contain hidden reservoirs of water ice? What is the origin of Mercury's magnetic field? Additionally, researchers are keen to investigate the peculiar hollows that dot Mercury's surface, which have sparked considerable curiosity within the scientific community. Launched on October 19, 2018, Bepi Colombo's journey to Mercury is anything but straightforward. The spacecraft is navigating a complex trajectory that necessitates a 7-year voyage, featuring an intricate series of 9 flyby maneuvers. These flybys include 1 at Earth, 2 at Venus, and 6 close encounters with Mercury itself. The purpose of these flybys is to gradually slow down the spacecraft, enabling it to counteract the sun's intense gravitational pull and enter a stable orbit around Mercury. During this epic interplanetary journey, the 2 orbiters remain stacked atop an ESA-built Mercury Transfer Module, or MTM for short. This module plays a crucial role in the mission, featuring an impressive span of 15 meters in solar arrays that harness sunlight to provide power during the transit. Interestingly, the MTM is equipped with 3 selfie cameras, originally intended for monitoring the deployment of solar arrays and antennas post-launch. However, these cameras have since become an essential tool for the Bepi Colombo team, enabling them to capture simple black and white images that document the spacecraft's location throughout its journey. Through these cameras, Bepi Colombo has been sending back what can be considered postcards from its encounters with various celestial bodies during the flybys. In April 2020, the spacecraft executed a flyby of Earth, coming as close as 12,700 kilometers from the planet's surface. This encounter allowed scientists to gather valuable data and further fine-tune the spacecraft's trajectory. Subsequently, in October 2020 and August 2021, Bepi Colombo made 2 flybys of Venus. The first encounter brought the spacecraft within 10,820 kilometers of the planet, while the second flyby took it a mere 550 kilometers above Venus's hot, cloudy surface. This close proximity enabled scientists to collect unique measurements of the planet's murky atmosphere, yielding insights that could enhance our understanding of Venus's climatic conditions and geological history. Once Bepi Colombo reaches Mercury, the MTM will separate from the 2 orbiters, allowing them to enter distinct orbits tailored for their respective scientific investigations. The MMO will settle into an orbit with a period of approximately 9.3 hours, while the MPO will orbit Mercury in about 2.3 hours. This carefully orchestrated separation is crucial for maximizing the scientific output of the mission. Bepi Colombo's operational lifespan is expected to last for 1 Earth year, equating to 4 Mercury years, with the potential for an extension of an additional Earth year, contingent on funding and the spacecraft's operational health. Simultaneously, another groundbreaking mission is unfolding: the James Webb Space Telescope. While James Webb is primarily designed to observe the cosmos in infrared radiation, illuminating the universe's history and the birth of stars, its capabilities also extend to the study of exoplanets, or planets that orbit stars outside our solar system. But how does James Webb analyze the atmospheres of these distant worlds? The process, though seemingly daunting given the vast distances involved, relies on specialized instruments and refined techniques. One such method is known as transmission spectroscopy. In this process, James Webb first observes the spectrum of the host star. When an exoplanet passes in front of its star, the telescope measures another spectrum. During this transit, the planet is backlit, allowing the starlight to filter through its atmosphere. Some of this light will be absorbed by the planet's atmospheric constituents, appearing as dips in the spectrum. By subtracting the star's spectrum from the combined spectrum of the star and the exoplanet, researchers can isolate the specific wavelengths of light absorbed by the exoplanet's atmosphere. They then compare these absorption features against extensive reference data that catalogs the light absorption characteristics of various molecules observed on Earth. This comparison allows scientists to determine the molecular composition of the exoplanet's atmosphere. One of the early targets for astronomers using the James Webb Telescope has been TRAPPIST-1, a small, cool red dwarf star located about 40 light-years from Earth. TRAPPIST-1 is home to a fascinating family of 7 small rocky planets, 3 of which lie within a region known as the habitable zone. This zone is characterized by conditions that are neither too hot nor too cold, allowing for the potential existence of liquid water, a crucial ingredient for life as we know it. However, analyses conducted using the Webb telescope on 2 of TRAPPIST-1's innermost planets, TRAPPIST-1b and TRAPPIST-1c, have revealed that they either lack a substantial atmosphere or possess only a very thin one. These findings raise questions about the habitability of these worlds and prompt further investigations into the remaining planets in the TRAPPIST-1 system. Dr. Joe Barstow, an astronomer at the Open University, remarks, TRAPPIST-1's system still looks promising if you are seeking a world that might support life, highlighting the ongoing intrigue surrounding this planetary system. Nevertheless, studying stars like TRAPPIST-1 poses unique challenges. Red dwarfs are known for their spotty surfaces, which can complicate the analysis of planetary atmospheres. Barstow notes, "Our own sun has sunspots associated with intense solar activity, but it has relatively few. By contrast, TRAPPIST-1 has dozens of spots that change all the time, making it difficult to differentiate between these and features of a planet's atmosphere. The TRAPPIST-1 system is not going to give up its secrets easily." Ultimately, astronomers employing the Webb telescope to search for signs of extraterrestrial life focus on identifying a set of biological markers known as the Big Four: oxygen, carbon dioxide, water, and methane. The detection of these elements in the atmosphere of an exoplanet would strongly suggest the presence of life. As the mission progresses, James Webb is expected to unveil a wealth of information about the chemistry of exoplanetary atmospheres, potentially leading to the discovery of bizarre and unfamiliar worlds. The future of James Webb appears promising and potentially lengthy. The observatory's launch aboard an Ariane 5 rocket from the ESA's launch pad in Kourou, French Guiana, was executed with near perfection. Webb utilized minimal fuel to maneuver into its intended orbit, a factor that augurs well for its operational longevity. Engineers estimate that the telescope's anticipated 10-year lifetime could be extended, providing additional opportunities for groundbreaking research. This extended mission duration means that astronomers will have the chance to delve deeper into the atmospheres of exoplanets, broadening our understanding of the universe. The excitement surrounding these explorations is palpable, as researchers anticipate uncovering strange and extraordinary worlds that challenge our preconceptions of planetary formation and habitability. The prospect of finding an Earth-like analog among the stars raises further questions about humanity's future in the cosmos. While the dream of interstellar travel is a popular theme in science fiction, the reality is that we currently lack the means to traverse the vast distances between stars. The closest star system to Earth, Proxima Centauri, is over 4 light-years away and would take the fastest spacecraft ever launched a millennium to reach, far from a feasible endeavor. Despite the allure of evacuating Earth, the sheer scale of interstellar travel renders this idea more fantasy than reality. Moreover, establishing a sustainable settlement on an alien Earth poses formidable challenges. Humanity struggles to create habitable environments even in low Earth orbit, on the Moon, and on Mars. The complexities of colonization are exacerbated by the lack of comprehensive knowledge regarding life support systems and long-term habitation in extraterrestrial environments. Therefore, while the search for Earth-like planets continues, the practicalities of interstellar migration remain daunting. Nonetheless, the significance of these missions transcends mere exploration. They tap into humanity's fundamental curiosity about its origins and place in the universe. For millennia, the question of how we came to be has inspired philosophical inquiry, religious reflection, and scientific investigation. As we gaze upon distant worlds through the lenses of advanced telescopes, we are not merely looking for planets. We are seeking to understand the processes that govern planetary formation, the conditions that foster life, and the unique characteristics that define our solar system and beyond.
Mercury, the smallest and innermost planet of our solar system, has long presented scientists with puzzling questions due to its extreme conditions and unique features. For decades, our knowledge of Mercury has been piecemeal, gained through fleeting flybys and occasional observations from Earth. But now, with the arrival of Bepi Colombo, the European Space Agency, and Japan's Aerospace Exploration Agency joint mission, the curtain is being lifted, and the planet is revealing itself in ways that have left scientists and space enthusiasts in absolute awe. Join us as we dig deep into the newest revelations about the Mercury that could blow your mind. To better understand the new discoveries, an overview of this extreme planet is needed. Mercury, as told, is the smallest planet in the solar system, with a diameter of just 4,880 kilometers, about one-third the size of Earth. It orbits closer to the Sun than any other planet, with an average distance of only 57.9 million kilometers. Its orbital period is just 88 Earth days, making it the fastest planet in the solar system. However, its day is remarkably long. One full rotation on its axis takes about 59 Earth days. Mercury's orbit is highly eccentric, meaning it is more elliptical than most planets. Its distance from the Sun ranges from 46 million kilometers at perihelion to 70 million kilometers at aphelion. This eccentric orbit, combined with Mercury's slow rotation, creates a unique solar day, the time from one sunrise to the next, which lasts 176 Earth days. Such peculiar orbital and rotational dynamics play a significant role in Mercury's extreme surface temperatures and the challenges of studying the planet. Mercury's surface is strikingly similar to that of Earth's moon, featuring a heavily cratered landscape dominated by ancient impact basins and scarps. However, unlike the moon, Mercury has some unique features, such as vast smooth plains and unusual geological formations known as hollows, which are believed to form from volatile elements escaping from beneath the surface. The Caloris Basin, one of the largest impact basins in the solar system, is a prominent feature on Mercury's surface. This 1,550-kilometer-wide crater was likely formed by a massive asteroid impact early in the planet's history, sending shock waves through the planet and leaving a complex terrain on the opposite side. Mercury's crust is made primarily of silicate materials, but its most distinctive feature is its high density. Despite being the smallest planet, it is the second most dense after Earth. This suggests that Mercury has a disproportionately large iron core, which makes up about 85% of the planet's radius. This large core likely plays a role in generating its magnetic field, but it also raises questions about the planet's formation. Mercury has a thin, tenuous atmosphere known as an exosphere, composed of atoms blasted off its surface by solar wind and micrometeoroid impacts. This exosphere is made primarily of oxygen, sodium, hydrogen, helium, and potassium. But it is so thin that it barely qualifies as an atmosphere in the traditional sense. This lack of a significant atmosphere means that Mercury's surface is directly exposed to space, contributing to its extreme temperature fluctuations. The planet's proximity to the Sun means that daytime temperatures can reach a scorching 430 degrees, while nighttime temperatures plunge to a frigid 180 degrees. These wild temperature swings are the largest in the solar system. Despite its small size, Mercury possesses a global magnetic field, which is a surprising characteristic. Most small, rocky planets do not maintain magnetic fields, as their cores have cooled and solidified. Mercury's magnetic field, though only about 1% as strong as Earth's, is still active, suggesting that the planet's core is at least partially molten. However, its magnetic field is offset, meaning that it is stronger in the northern hemisphere than the southern, which presents a puzzling question about how such a field is sustained and how it interacts with the solar wind. Mercury's internal structure is another source of scientific curiosity. The planet's large core is believed to be composed mostly of iron, surrounded by a thin silicate mantle. The exact nature of Mercury's core remains a mystery. It is unclear whether it is fully or partially molten, and scientists are still debating how this core formed. One hypothesis suggests that Mercury was originally much larger but lost much of its outer layers due to a massive collision early in the solar system's history. Bepi Colombo aims to provide further insight into this by measuring the planet's gravity field and magnetic properties. Despite its relative proximity to Earth, reaching Mercury is one of the most difficult feats in planetary exploration. While it may seem counterintuitive, Mercury is harder to reach than some of the planets much farther from Earth, such as Mars or even Saturn. This is because the closer a planet is to the Sun, the more its motion is dominated by the Sun's massive gravitational field. Mercury orbits just 57.9 million kilometers from the Sun, a distance that places it well within the Sun's gravity well, meaning that spacecraft sent to Mercury must contend with the overwhelming gravitational forces that continuously try to pull them toward the Sun. To reach Mercury, spacecraft must slow down significantly as they approach the Sun. This requirement contrasts with missions to outer planets, where the primary concern is gaining speed to escape the Sun's gravitational pull. Essentially, a mission to Mercury involves slowing down enough to fall toward the planet without getting pulled into the Sun. However, slowing down in space is one of the most energy-intensive maneuvers for a spacecraft. Objects in the inner solar system travel at incredibly high velocities because they are constantly orbiting the Sun. Mercury's orbital speed is approximately 47 kilometers per second, much faster than Earth's 30 kilometers per second. A spacecraft traveling toward Mercury must match this high velocity to enter orbit around the planet. Achieving this involves a delicate balance of maneuvers, including gravity assists, to gradually reduce the spacecraft's speed as it falls deeper into the Sun's gravitational influence. Traditional propulsion systems struggle with this challenge, as they are typically optimized for boosting a spacecraft away from Earth, not for decelerating a spacecraft close to the Sun. This deceleration is essential because, without it, a spacecraft would either miss the planet entirely or be pulled into the Sun's gravity and crash. As a result, a direct route to Mercury would be too fast for a successful orbit insertion. One of the most effective ways to slow down a spacecraft en route to Mercury is by using gravity assists, also known as gravitational slingshots. These maneuvers involve flying by other planets, allowing the spacecraft to gain or lose speed by borrowing from the planet's momentum. In the case of Mercury missions, gravity assists are typically used to decelerate the spacecraft. The European Space Agency's Bepi Colombo mission, launched in 2018, is a prime example of this technique. To reach Mercury, Bepi Colombo performed a series of 9 gravity assists, 1 around Earth, 2 around Venus, and 6 around Mercury itself. These assists helped the spacecraft gradually shed speed, ensuring it would arrive at Mercury at just the right velocity to be captured by the planet's gravity. Without these gravity assists, a spacecraft would need an enormous amount of fuel to decelerate, making the mission impractically expensive and complex. Gravity assists allow mission planners to take advantage of the natural dynamics of the solar system, but they come at a cost: time. Missions like Bepi Colombo take years to reach Mercury because of the numerous flybys and the looping trajectory needed to gradually slow down. In Bepi Colombo's case, the journey to Mercury will take 7 years from launch to orbital insertion, with the spacecraft expected to enter orbit in late 2025. Beyond the challenges of navigation and orbital mechanics, missions to Mercury must also contend with the extreme conditions near the Sun. As spacecraft approach the Sun, they are exposed to intense solar radiation and heat. To survive these conditions, spacecraft must be designed with advanced thermal protection systems. And even after overcoming the hurdles of speed and heat, the final challenge in reaching Mercury is achieving a stable orbit around the planet. The Sun's gravitational field is so dominant in this region of space that any miscalculation in speed or trajectory could cause the spacecraft to either miss Mercury entirely or crash into the Sun. Orbit insertion around Mercury requires precise timing and velocity adjustments. A spacecraft must arrive at just the right moment and at the correct speed to allow Mercury's gravity to capture it without pulling it into a collision course. This maneuver, which often involves firing the spacecraft's engines for an extended period to further slow it down, is a critical moment in any Mercury mission. But despite these significant challenges, the Bepi-Colombo mission is poised to build on the success of previous missions and provide unprecedented insights into Mercury. One of the primary goals of Bepi-Colombo is to study the mineralogical and chemical composition of Mercury's surface. Unlike Earth, Mars, and Venus, Mercury's surface lacks the dense atmosphere needed for significant weathering processes. This means the planet's surface can offer a relatively unaltered record of the solar system's early formation. Bepi-Colombo's suite of instruments, including the Mercury Imaging X-ray spectrometer, has started providing insights into the mineral composition of the planet. Preliminary findings suggest a surface that is rich in magnesium and sulfur, confirming earlier data from MESSENGER, but with new, unprecedented resolution. These minerals suggest that Mercury might have formed in a much different environment compared to the other rocky planets. Interestingly, Bepi-Colombo has also identified new elements like sodium, calcium, and potassium in higher concentrations than previously observed. This discovery indicates that volatile substances, those that evaporate easily, are present in larger amounts than once believed, challenging the assumption that the planet's proximity to the Sun should have stripped it of most of its volatiles during formation. One of the more intriguing discoveries from previous missions is that Mercury is a shrinking planet. As it cools, its iron-rich core contracts, causing the surface to wrinkle and form scarps, steep cliffs that run across the surface. Bepi-Colombo has provided new, high-resolution imagery of these tectonic features, some of which are over a mile high and stretch for hundreds of miles across the planet. What's remarkable is that Bepi-Colombo's observations indicate that this shrinking process may still be ongoing. Previously, scientists believed that this contraction mostly occurred billions of years ago. However, the presence of relatively young scarps, some of which appear to have formed within the last few 100 million years, suggests that Mercury is still tectonically active. This finding is significant because it implies that Mercury, unlike most of the other terrestrial planets, may still be geologically alive, albeit in its own unique way. In addition, Bepi-Colombo also has been actively studying one of the most groundbreaking discoveries made by MESSENGER, that Mercury has a surprisingly strong magnetic field. That itself is unusual for a planet its size. And what Bepi-Colombo found is just adding further complexity to the mystery. Bepi-Colombo's instruments, like Mercury Magnetospheric Orbiter, have revealed that Mercury's magnetic field is not only surprisingly strong, but also highly asymmetrical. The magnetic field is significantly stronger in the northern hemisphere than in the southern, a phenomenon that had been previously noted but is now much more clearly observed thanks to Bepi-Colombo's precision. This asymmetry suggests that Mercury's dynamo, the process by which its molten core generates a magnetic field, operates in a manner quite different from Earth's. The mission's data is beginning to provide clues that may help scientists better understand how magnetic fields arise in planetary bodies and why Mercury's magnetic field behaves in this strange manner. For example, the composition of the core, the speed at which it cools, and the planet's peculiar spin dynamics might all play a role. Besides the magnetic field, Mercury's exosphere also is a remarkable aspect. Mercury, as we know, despite lacking a thick atmosphere, has what is known as an exosphere, a tenuous cloud of atoms that are constantly being stripped from its surface by solar wind. Bepi Colombo's instruments, particularly the Mercury plasma particle experiment, have begun providing new insights into how the solar wind interacts with Mercury's surface and exosphere. What Bepi Colombo has revealed so far is that these interactions are far more complex than previously thought. For example, the data shows that the solar wind accelerates particles from Mercury's surface into space at speeds higher than predicted, creating a dynamic environment around the planet. Moreover, the composition of the exosphere, dominated by sodium and oxygen atoms, varies significantly based on Mercury's distance from the Sun, which fluctuates due to its highly elliptical orbit. Additionally, Bepi Colombo has detected bursts of energetic particles that are likely caused by the solar wind interacting with Mercury's magnetosphere, leading to brief but intense outflows of particles from the planet's surface. These findings are crucial for understanding space weathering processes not only on Mercury, but also on other airless bodies in the solar system, such as the Moon. Elsewhere, Bepi Colombo also focus on finding water in that planet. Despite its scorching surface temperatures, Mercury is home to deposits of water ice, which are believed to exist in permanently shadowed regions within craters near its poles. Bepi Colombo has started to shed new light on these icy deposits, building on discoveries made by MESSENGER. Bepi Colombo's Mercury radiometer and thermal imaging spectrometer provides temperature maps of the planet's surface, including these shadowed regions. Early data suggests that the ice deposits are more extensive than previously thought, and some areas that were assumed to be too warm to support ice might actually harbor small amounts of frozen water. This discovery is reshaping our understanding of how ice can persist in extreme environments. What's particularly interesting is that Bepi Colombo also analyzes the composition of the material mixed with the ice. Some scientists theorize that this material could be rich in organic compounds, which might have been delivered to Mercury by comets or asteroids. If confirmed, this would add an exciting new chapter to the story of how water, and possibly even the building blocks of life, might have reached the inner planets. The last one in Bepi Colombo's list of primary scientific objectives is to investigate the origins of Mercury. The planet's high density, coupled with its relatively thin crust, has long puzzled scientists. Bepi Colombo's early findings are already challenging long-standing theories about how the planet formed and evolved. For instance, one prominent theory suggests that Mercury formed much farther from the Sun and was later pulled into its current orbit by gravitational interactions. Alternatively, some believe that Mercury may have once been much larger, but lost much of its outer layers during a catastrophic impact early in its history. The high-resolution imagery and compositional data from Bepi Colombo are beginning to reveal new clues that could support one of these competing theories. Early observations suggest that Mercury's composition is markedly different from that of other terrestrial planets, with a much higher concentration of iron. This supports the idea that Mercury might have experienced a violent collision that stripped away its outer mantle. However, the presence of volatiles challenges this view, as such an impact should have vaporized these elements. In short, as you see, although Bepi Colombo has only just begun its mission, and already, the spacecraft is already reshaping our understanding of Mercury. From new insights into its shrinking surface and mysterious magnetic field, to fresh data about its volatile-rich exosphere and icy poles, Bepi Colombo is providing scientists with unprecedented views of the solar system's innermost planet. In the coming years, Bepi Colombo will delve even deeper into Mercury's mysteries. As it continues to map the planet, measure its magnetic field, and analyze its surface composition, we can expect even more groundbreaking discoveries. These findings will not only illuminate the secrets of Mercury, but also offer new insights into the formation and evolution of rocky planets throughout the galaxy. What's notable is not only Mercury, but Venus is also on the must-explore list. While Mars is small, distant, and cold, and Mercury is scorchingly baked and atmosphere-free, Venus represents an interesting case of an alternative pathway for an Earth-sized planet. Although Venus is about the same physical size as Earth and only somewhat closer to the Sun, any Earth-like conditions once present on it have been left in the distant past. Today, Venus has a thick, cloud-rich atmosphere of dense greenhouse gases, with surface temperatures hot enough to melt lead and tremendous evidence for copious volcanic activity. Although it has no active, moving tectonic plates today, a new paper argues that Venus, like Earth, once possessed active plate tectonics. But does it hold true? Let's find out. First, accept that there's a lot we still don't understand about plate tectonics, both on Earth and elsewhere in the solar system. On Earth, we understand that our planet's lithosphere, the combination of our crust and the mantle's topmost layer, are fragmented into a series of plates, which in turn collide, spread apart, uplift, and subduct, among other behaviors, creating a rich diversity of surface features. These can include new land masses, large mountain ranges, and can even recycle old sections of the Earth's surface back into the planet's interior. This is certainly true of modern-day Earth, but did our planet always possess the plate tectonics we're accustomed to at present? That question is far more uncertain, with no consensus within the community as to whether plate tectonics are basically as old as the Earth, whether they began hundreds of millions or even 1.5 billion years after Earth's formation, or whether they only came about relatively recently. From looking at other worlds in the solar system with ice plate tectonics, such as Europa and possibly even Pluto, it may be that the combination of internal heat, along with the lubricating effects of water, are what enable the plate tectonic behaviors that are present on Earth today. It's a pretty good bet that Mercury, our Moon, and Mars all never had plate tectonics on them, for a variety of reasons. For Mercury and the Moon, the weight of evidence from craters and cratering rates support the notion that no tectonic activity was ever present on them, and Mercury itself even lost most of its mantle early on in our solar system's history. It has the largest metallic core of any planet relative to its size. For Mars, meanwhile, the fact that it has only a few notable volcanoes, and that the volcano-forming hotspots beneath its crust are still in the same location they were 3+ billion years ago, constrains any plate tectonic scenario to its most extreme early stages. It's enough to make one wonder what it is about Earth, if anything, that makes our planet special. These other worlds show no evidence for plate tectonics in either recent or ancient history, and in fact may all have been uniplate planets for all of planetary history in our solar system. But in order to even consider that Earth is something special here, we need to consider the curious case of Venus. Venus is comparable to Earth in terms of both mass and physical size, and is currently volcanically active today, with recent evidence emerging from the Magellan mission suggesting that volcanic eruptions are still occurring there and creating local resurfacing events at present. However, when we examine the surface of Venus and look at the cratering rates on the surface of that world, we can conclude that 80% or more of the Venusian surface is young, only about 1 billion years old at the oldest. This means that for most of Venus's history, the first 3.5 billion years of its planetary history, we have practically no information about what its surface was like. How, then, can we be expected to draw conclusions about Venus's history and whether it had plate tectonics or not, particularly when Earth's early tectonic history, even with all the data we have about our planet, is still in doubt? It's a challenging proposition, to say the least. Keep in mind that unlike the Earth, for Venus, we have no rock samples from it, no high-resolution mapping of its surface, and only a limited geologic record. that only goes back to cover approximately 22 to 25% of the planet's total history. Even with that, Venus, as we observe it, shows a pattern of tectonic deformation and may indeed have a globally fragmented and mobile lithosphere, despite not having Earth-style plate tectonics right now. The answer, as counterintuitive as it may seem, might be something we can learn by examining Venus's atmosphere, rather than anything occurring on, or even beneath, Venus's surface. One of the key reasons this may be possible is that the interior evolution of Venus is directly related to the evolution of Venus's atmosphere, with the gases and atomic components of gases that make up its atmosphere primarily originating from within the interior of the planet itself. If you can take a look at what Venus's atmosphere is like today, for example, and compare it with various models that take into account the interplay of Venus's atmosphere with the thermal, just heat contents of Venus's interior, the chemical evolution of Venus's interior, and the tectonic evolution of Venus's crust and upper mantle, then it may become possible to look at the atmospheric contents of Venus today, including the quantities of gases like molecular nitrogen, carbon dioxide, and anything that contains sulfur, and consider which models are consistent with the data and which ones conflict with it. That's precisely what this new paper seeks to do. We know that Venus, as our starting point, is nearly as large and massive as Earth and is composed of very similar materials on the inside to our own planet, as evidenced by Venus's similar density to Earth. The comparison is 5.24 grams per cubic centimeter for Venus overall versus 5.51 for Earth. If that's the case, then much like Earth, Venus must have formed with a substantial amount of internal heat, and should also possess similarly sized layers to Earth, a solid, iron, metal inner core, and, perhaps, an innermost core within that as well, surrounded by a liquid iron metal outer core with an enormous solid rock mantle outside of that, composing most of the planet's volume, followed by a thin crust. With all of that heat inside all of those layers, it's a near certainty that the mantle itself is going to have an enormous temperature gradient within it, and that temperature gradient is going to lead to some sort of convective or churning over behavior. However, the big uncertainty involved with Venus, which also concerns uncertainties when we consider Earth's ancient past, is just what type of convection occurs within it. Does the whole mantle convect? Does the mantle convect in separate layers, and do those layers mix? And does any part of the mantle that convects include the surface crust, allowing the surface to participate in what's called mantle overturn or not? Here on modern Earth we have upper mantle convection, which includes the overturn of Earth's crust, along with the upper layer of Earth's mantle. Lower mantle convection, which involves the asthenosphere but not the lithosphere, and also whole mantle convection, all occurring simultaneously within our planet. However, on modern-day Venus, it's thought that this is not occurring. Instead, present-day Venus has what the geophysics community calls a stagnant lid, which means that the topmost layer of the planet, the lithosphere that includes the crust and the uppermost mantle, is cold, solid, and relatively stable and immobile. This leads to stagnant lid tectonics, which includes virtually no horizontal side-to-side motions, which means that even if the lithosphere is fragmented into plates, these plates don't migrate across the planet's surface, but rather stay in place. As you may have guessed from noticing that hot lava flows, but that colder rocks do not flow, a cold, solid lithosphere would be very strong and not easy to break apart, which would mean that any lower mantle convection wouldn't affect the stagnant lid very much at all. Today, Venus very much has a stagnant lid. Early on in Earth's history, before achieving our present state of active plate tectonics, which is sometimes called mobile lid or active lid tectonics, we may have also had a stagnant lid on our world, It was recognized as early as 1989 that the stagnant lid regime is a very stable configuration and may have even applied to Earth long ago. But did Venus always have a stagnant lid? For nearly 30 years now, it's been pretty clear that the data we've acquired only allows us to say that the stagnant lid phase of Venus is at least around 500 million years old, but that early on, this may not have been the case. Just as Earth may have switched modes in its ancient past, so too may have Venus, as its young surface offers little in the way of constraints on its early properties. But this is why Venus's atmosphere is so interesting, because it's thick and massive, but not so thick and massive as to have turned Venus into a mini Neptune-like world. At its surface, Venus has 93 times the atmospheric pressure as there is at Earth's surface, with a whopping 4.8 x 10 to the power of 20 kilograms of mass composing the Venusian atmosphere. For comparison, that's about 40% as massive as all of Earth's water stores, including the oceans combined. Venus's atmosphere is made up mostly of carbon dioxide, 96.5%, and nitrogen, 3.5%, with the next most abundant component, sulfur dioxide, coming in at only 0.0015%. The big question that the authors of the latest study looked at is, based on a realistic thermal model for early Venus's interior and either stagnant or active lid tectonics, how much nitrogen and carbon dioxide would have been produced? If there was a stagnant lid the entire time that Venus has been around, there's no way to arrive at the present amount of nitrogen, or the present amount of carbon dioxide, or the present amount of total atmospheric pressure that Venus exhibits today. On the other hand, if there was an active lid for too long, for about 2 billion years or more, on Venus, then you would actually wind up overproducing the gases we see, particularly carbon dioxide. It's an implausible scenario that Venus would have been a planet with active lid tectonics for most of its history. Instead, what you want to do is match all three observables: nitrogen abundance, carbon dioxide abundance, and total atmospheric pressure, even when you account for solar and planetary evolution and how they affect a planetary atmosphere over time. The scenario that best matches the data, according to this latest study, is one where Venus possessed an early, active phase of plate tectonics that produced large amounts of nitrogen and carbon dioxide early on, lasting for around the first 1 billion years, and possibly slightly more, of Venus's history. This had to have been followed by a transition from active lid to stagnant lid tectonics, what the authors call a great climatic tectonic transition, where the stagnant lid mode then persists up through the present day. Although the stagnant lid mode still includes volcanic activity, the outgassing rates are greatly reduced over the active lid scenario. This paints a novel but grim picture of how Venus came to be the way it is today. Perhaps early on, the active lid tectonics released large amounts of carbon dioxide gas, and that gas may have accumulated rapidly in the atmosphere. If you can't recycle, lose, or sequester that carbon dioxide fast enough, it leads to an extreme greenhouse state, and that's a fatal condition for any surface-dwelling life. However, if life arose early enough on Venus, before the runaway greenhouse process, it's still possible that life's vestiges still exist in Venus's atmosphere today, and could potentially be detected by probing carbon and nitrogen isotope ratios. Whether there was life or not, the Da Vinci mission, among others, will be able to measure the nitrogen-15 to nitrogen-14 ratio, which will help determine how much atmosphere was lost to space over Venus's history. But most importantly, in the history of plate tectonics, we know that Earth is no longer alone in the solar system. Venus once had active plates too, and its atmosphere, not surface, is what lets us know for sure. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.